So, welcome everybody. Our next speaker is Christian Gross from the University of Tübingen, and he's going to talk about programmable quantum scheme models with Rydberg.
Yeah, good morning, everyone, and thanks for the invitation to this workshop. Unfortunately, I could only come actually, well, today due to teaching we still have in Germany, but I'm already enjoying it since this morning. So I want to talk about our kind of recent work about realizing, or let's say, putting as much as programmability as you can think of at the moment for analog quantum simulation with Rydberg arrays. That is actually work that we have still done in the last month before we disassembled the experiment in Munich. Yeah, let's go through. So the outline is, I will give you a short introduction motivating actually our work. Then I want to try to explain you the method we are using, basically as Rydberg Dressing, we are using to design the interactions. And you will see that we are not yet there, that we have this method like fully under control in terms of coherence. What we see is spin flip rates, and I will discuss a little bit the coherence limits that we have. Yeah, so why is this interesting? This is interesting because of, well, it's interesting per se, of course, being able to design spin Hamiltonians more or less at will. But also, there are so many experiments popping up in the world with tweezers. Well, it would be very nice to have basically, you know, enough workspace for all of them. From experimental point of view, it's really about also finding niches there for the different experiments. And if there are experiments here actually that I have not yet on that slide, don't jump on me, but tell me, I will put it on. Yes, so, what I don't have on here is this big N of academic setups that are in preparation. It's probably 50 or more, plus all the company setups that Mark was given an example just this morning. So the toolbox we have in this array, I mean, there's a reason, of course, why these arrays are so effective, because we have a very nice toolbox. And they're interesting for both fundamental physics and then prospectively for quantum technologies. So what we have is, first of all, we have really a large atom order, like more than 100 simulators that are very nicely controlled, a large atom number. We have very nice detection capabilities. Basically, one by one, we can detect in sequence, as Mark was reporting. The detection can be very fast. This is a new development that Manuel basically, I guess, reported. And we have very nice control capabilities that are in principle nicely coherent. We can control interactions, the single particle terms, again, one by one. And we can control the connectivity of these arrays, of course, by positioning. So the question is really, what can we do with this platform? So where are the limits, basically? And then there's, of course, this big research line basically driving them towards really fully digital quantum computation. And the other line is, of course, analog quantum simulation. By the way, what is very nice with this platform is these are not mutually exclusive. They are more or less have the same technical underpinnings that you have developed in the lab. Then in the analog quantum simulation, that's really the motivation for this talk and for our work here, is we want to go a little bit beyond, like, let's call it self-simulation of the machine, right? We want some tunability, some control, some programmability of your simulator to make it more versatile. And for those qubit-based simulators that we are talking about here, well, one thing that comes to your mind that would be cool actually, if we can realize spin Hamiltonians where we basically can more or less freely control the strength of all the different spin interactions here. And I only write down the interaction terms, of course, simply single particle control you can add on top. So these neutral direct arrays, I think also Mark mentioned that they really got the boost, let's say, with the invention of this dynamical positioning and also, yeah, basically not even in sequence but sorting, such that we can make really large arrays without positional entropy. And that was really, for me, it was basically the start of this platform that was achieved in Korea, Harvard, and Paris. The other ingredient is fundamental to make many-body physics on these models is of course, the coupling to the Rydberg states. And coupling to the Rydberg states is also kind of flexible in these models, because you have, or in these systems, you have quite some choices where you have different, let's say, advantages and disadvantages. So one thing where we actually are concentrating on here is the direct coupling from the ground state via a UV photon to a Rydberg P state. Advantages: you don't have an intermediate state, and you don't go actually for intermediate state scattering. That actually has been found in Misha's group to be a little bit found and solved to be limiting to gate fidelities in the 99-point-something regime. The other scheme is the two-photon coupling that actually also has some advantages, because of you will have lower coherence than you would figure, but you can choose this detuning, and in this case, if you really adjust the time scale of your coupling. So depending on what you want to do, this can be a very big advantage that you cannot have here. And then, of course, coherent here is a big word, and I think I will have on the very last slide, I hope I make it there, a little bit comments on that, but Mark actually commented a lot about the importance of laser noise that is really key in this systems. And then when you Rydberg states, what you typically play with is, of course, actually we play typically with the asymptotic form of the long-range interactions that you get. And then between two Rydberg states of opposite parity, what do you get? You typically get flip-flop type Thunderbolts 1/r cube interactions. And between Rydberg atoms in one state, the direct dipole is of course forbidden. So what you get is the next order, which then amounts to Thunderbolts 1/6 interactions. So these are the natural interactions I would say you get in this systems. And then actually with this you can realize x, z, and x, y, z Hamiltonians if you play with two states in the Rydberg manifold. You typically get Ising if you play with the state in the Rydberg and the state in the ground state. And actually there's like a paper of 2 days ago from Jerry Barnes' team where you can show that with this one you can also realize quite strongly anisotropic Heisenberg models. And when you go into the dressing paradigm, that means you admix Rydberg states only a little bit, then actually this is the regime where you can really get designable interactions, Ising, X, Y, Z, quite a bit, whatever you like. Okay, so let's walk through the idea of Rydberg dressing by interaction design. So first of all, let's play just with the natural occurring interactions and work and admix them to the ground state. That's a little bit the idea, or let's see what we can do with the natural occurring interaction. So one way is actually in this realm where we have an XY model on the Rydberg manifold. We have very nice microwave control between these two states, and we have the possibility to drive very fast. And this is actually what was demonstrated in Matthias Weidemüller's group, and then used also, and now it's still being used and being used more and more in Antoine's group to basically play with locally engineered XYZ models. The other possibility is what I started explaining just at the beginning is this Rydberg dressing, where you have an adiabatic way of designing the interactions by mixing basically Rydberg character into ground states. And the nice thing is now all of your physics happens in the ground state. You have absolutely no problem with spin rotations, measurements, and whatever basis you like, and so on and so forth. So it comes with a lot of advantages if you get this scheme actually under control. Yes. So the simplest setting for this Rydberg dressing is basically when you aim at an Ising model. And then the idea is basically, well, you mix a little bit of interaction to your one of your two spin states. Then when two atoms come close, well, that state sees interactions, means basically its energy is conditionally shifted up on the state of the second atom. And if you write that down in an Ising model, the shape of these interactions are also pretty intuitive to understand. So what you get is basically you have a laser that is detuned by delta to the two atom pair state up here, which has now this standard asymptotic form that I've drawn here. And then you have some admixture in the asymptotic regime, and you have basically no admixture anymore to the two atom state in the very close distances, just because of the interaction is basically infinitely far. You infinitely far away, and that explains you that for some short distances you will get a leveling of the interaction, and at long distance you will have something else and interpolate that, and you get a soft potential that you typically get. And this is something that we started to explore actually in Munich already, and Johannes was talking earlier this week. I think he also talked a little bit about Rydberg dressing. And we started to explore in 2016 already, and we could actually show that this engineering works, and that we can deduce basically in a coherent fashion correlations in such actually in an optical lattice force. I was thinking, or I was hinting at more actually. I was hinting at that we want basically freely controllable also in the shape of the interactions. And one way of basically controlling the shape of the interactions is actually going to closer distances, such that the pair interaction potentials look more complicated, and in particular can also get crossings of the pair interaction potentials. This is such an example. It's an example that we actually explored also in Munich in an optical lattice, where we basically did spectroscopy of in such a configuration here, the lattice spacing of 750 microns. We basically tuned our laser, and what we saw was basically a series of resonances, which came out to be very nicely evenly spaced, and we identified them basically as the vibrational levels of Rydberg macrodimers. So these now you can use to dress to them. So the idea is basically now your off resonance we couple it to this, for example, this upper parabola of this naturally occurring level anti-crossing. And when you calculate what you get out, you get a very peaked interaction profile. So what is shown here is basically the comparison of standard dressing, the gray one, to the avoided crossing dressing, macrodimer dressing, which is the blue one. And actually, the dots are where we stand with this point, with this potential with the optical lattice. So this gives you a scale. Optical lattice distance is should be 500 nanometer. So this let's say width of the potential is more in the order of 50 nanometers. So get very sharp control over induced interactions. And this we tested in the optical lattice, basically in the Ramsey sequence. That was the way the experiments, the correlation that I've shown you before was also done. So basically, you put the atoms in a superposition of the two ground states. You switch on your interactions, then you aggregate because of the typical problems with single particle rotations. You dress again, and you measure basically the resulting state G2 correlations, and you see basically that you get correlations very sharply only between two lattice sites here that grow with time. Then you can check how they grow, and you see some hints that this starts to be actually in the coherent regime. So first of all, it's I think it's a quadratic start. Second of all, there's a start of the turnover that so actually the same, this is also something that I want to mention. The same technique is used by Harry Gott and Kaiserslautern by dressing actually to these ultra long molecules and inducing basically then what he calls an optical patchwork resonance in the ground state. And he does these experiments in the continuum, or he introduces interactions potentials not in the ground state but in the first excited states, and gets then basically designer molecules between these rubidium methods. So this is very related work that I think should also be mentioned in this context. So now let's come. How am I doing? Good. So so let's reduce time to pass. Let's go. Let's go. Let's really come to our work now that we have done in the visa array. And that is really interaction design by double Rydberg Dressing. So the setting is what we aim at is we want to control such an XYZ model, which I have written here and also have written before, as basically the Ising term, and then you can rewrite the XYZ, of course, as a flip-flop and a flop-flop. And if there's an X not equal C, there's a finite flop-flop in this term. The finite flop-flop term is there. And in the way of what I've demonstrating for the Ising model, what we also aim at is spatial control basically of this interaction coefficients. One important thing that you should keep in mind now in the entire nomenclature that I use now to describe physics is that we need a setting where we by basically laser selection rules couple our upspin state to something that we call the Rydberg upspin. But there is no cross coupling between the red and the blue. So the dark coupling on the single particle level. This we do by polarization selection test. I will show you effectively that we get around the process, but that will be entirely enabled because of these levels here are not anymore the pair levels, but they are basically by the pair interaction mixed levels. And this is actually coming now. So the idea of inducing these interactions is to really make use of the complex level structure that we have there, pair interaction level structure that we have in the Rydberg atoms at, let's say, not asymptotic distance, so somewhat closer. And what close and not so close means, of course, it depends on the Rydberg insulator. And what we then explicitly use is basically the decomposition of the pair-eigenstates into the pair Rydberg states, and for these pair Rydberg states, you know our laser selection rules. But if we couple, for example, to that state, let's say we couple to this up state, then because of this eigenstate also contains a down-down amplitude, it allows us to couple down on the down-down leg just because of the interaction. This state is that. So this is the fundamental idea. If you get this idea, the rest is basically standard. And of course, to calculate all of this, we really heavily rely here on these two nice open source packages, which you can get actually the lineages. So let me. In pair state 2, and what we have to do is actually we have to bring the two atoms basically virtually up to the excited state and then bring it down to the ground state. And if you draw it like this, like a lambda scheme, then you know directly well the population should be something like the Rabi frequency on leg 1 times the Rabi frequency on leg 2 divided by 2 times the detuning. And the detuning now involves basically the Van der Waals interaction, and so it's a detuning to the pair states here. In the end, we also have some order. Let's go through an example of the flop-flop interactions. So our ground states are now 2 atoms up, 2 atoms up, and we want to turn them into 2 atoms down. So what to calculate now this fourth order perturbation? Let's do that again, right? For the poor experimentalists. I can again do adiabatic elimination on the single leg, basically, so only one leg. I have now a single atom detuning here from the upper state. And then I'm popping up to the final state. I can write down the object state. I mean, this is one laser, this is the other laser. Of course, we have to have energy conservation, and these levels here are in principle not on the same energy. And that means, of course, that we need to have the laser on something like a Raman resonance. So I put it in other codes because there's no Raman single atom resonance. It's just what I need is basically that these energies to measure. So now, going on. Using to move. Okay. With the danger that you get bored, flip-flop interactions have one peculiarity. So let's say you want to go from up down to down up. First of all, there's no Raman resonance condition because they are both on the same level. And actually, flipping them up and down involves one laser and the other laser in the symmetric way. But what you have now is you have actually two paths. So you can either first go up with the blue atom and then with the red atom to Rydberg blue, Rydberg red, or the other way around. And of course, you have to add two paths. And when you add the two paths, then you can actually have destructive interference already on one leg. And you have actually a way of switching off your flip-flop interactions while nothing happens for the flip-flop interactions on the same detuning exchange. So this is a way of controlling one of the terms against the other two. Yeah? And that happens due to the interference on one path. And then just to wrap this whole story up, this example of the flop-flop interactions that we let go through in detail. What you get if you look at the formula, first of all, these CKs, they are in principle distance, angle, and then of course rows that flip, flop-flop, and so on dependent. And the second thing that you have, what you can play with, is the sharp control feature is you can go close to the stair state. So we have basically resonances down here, with which you can resonantly enhance one or the other of these interactions. And to show you an example of what control we get, I show you these two control landscapes. So basically, we plot here the ratio of the flip-flop towards to the icing and the flop-flop to the icing interactions, and just change the distance of the atoms. That is what is meant here with this P and theta we can fix. And you see, we can basically cover the entire plane here. Or we can change the angle between the interactions and again cover more or less the plane. I mean, this is hard to block because you have really a lot of really freedom to play in this system. So now how do we probe that? We probe that in our potassium 39 Visa microscope, where we have nice single atom control. We do it in spatial light SLM-based Visa array. As I said already, it's a UV laser that we couple it to the Rydberg state. And then in this special experiment, okay, so in this specific experiment, we just want to show basically that we can control these interaction processes. So what do you do in the experiment? You basically groups of 3 tweezers. We don't have this sorting yet under control, so they are randomly loaded. But what we can control in these groups is basically the orientation towards a quantization axis given by the magnetic field, basically. And with this, you can test the angle and the distance. Of course, we can stretch that dependence. The groups are spaced by more than our interaction distance in the problem. So that's just statistics trick. Just to be complete, I emphasize there's no Raman condition. So what we do is actually we use sigma, cleanly sigma minus polarized things on these two levels connecting to these Rydberg states such that there is then no lambda process here directly possible on the single scheme. And of course, we test that experiment. So now how do we read out? That's pretty much standard. I think I can walk pretty fast through. So we take our first image, which we record basically, checking basically the initial loading of the system and all atoms here in one of the 2 states. We do the physics, we blow out that state, and those atoms that survive have to be in another state. So then with this, we don't have actually individual control, we always start in one state. So now you might think, how can they even test flip-flop interactions? We cannot because of the beginning polarized, so that channel is not there. But what we can see the flip-flop interactions if they are actually better than the flop-flop interactions. And if we know that we don't have flop-flop interactions, like at the distance of 2, but we go now and we check, we go from some image like this, where we have basically 2 atoms there, to 2 atoms like this. This is actually a combined flip-flop process. Okay. Start it again.
You need some water.
And with this, you can approach the individual processes. So I want to show you that we really can see the flop-flop process and the most, let's say, qualitative thing you can test with the flop-flop process is really the presence of the Raman condition that we need to fulfill. So basically what we do here is we check for processes that bring us from up to down, versus basically the detuning of the 2 lasers, the difference of the detuning of the 2 lasers. And we see basically a very narrow response here. And you have already seen something here. This is we call this here, the scale is 1%. That has something to do with my rate comment at the beginning. Now let's test we fix this condition and then test actually for basic distance and angle selectivity. And what we do now is basically we turn these groups versus the magnetic field here on that basically in this direction 90 degrees means basically 90 degrees to the magnetic field. This means the let's say line of tracks is aligned with the magnetic field, and then we can turn them continuously, or we can change the distance between these tracks, and then check for the flop-flop processes we see. And by the way, this is tuned such that we do not have flip-flop, and we also don't see flip-flop. I don't show it here. And then what you see basically when we test versus distance, then I should say the underlying color plot is the theoretical prediction of the strength of this plot term that we get here. We basically see a very nice match with the theoretical prediction from our data points. And if I say something like this, I made a comment about the probability. It's a very nice match if you put an arbitrary touch factor on the amplitude of the field. Yeah. This is something that is important to keep in mind, and I will address this specifically. If we tune angle, actually the most qualitative feature that we see, we should actually have a resonance where this delta 2 thing that I had in the formula, basically what you do, you hit the pair state. Yeah. And then the interaction strength basically diverges, and actually our conservative model of those lines. But we see this actually that we have basically a very strong response at the right spot. Flip-flop interactions you can also test for, and keep in mind this is always flip-flop, so we have to make sure that there is some flop-flop. It's very dangerous for that there is some flop-flop that we actually have a chance to see on flip-flop. Because otherwise our initial state is wrong, so to say. So we do basically the same experiment. We tune first versus angle versus distance along that line, and we basically see the feature. So actually here we have two resonances that we cross. Our data points scatter is a bit suggestive block, I have to admit. Our data points they scatter a bit widely here. But we see a response in the right region. And maybe this is an important thing to show. If you really scan the angle through where we do not expect anything, we basically don't see it. Now, I was emphasizing multiple times the tiny rates that we see in the process. And that is, of course, something that bugs us experimentalists a lot, because you make this nice story about the spin models, and then basically you see something, but you see basically epsilon. So what's the issue? The issue is really we are running into several coherence limits actually at the same time. So first of all, let's say motivate a little bit this Rydberg dressing story. Actually, especially connected with dressing in the non-standard way to these directly addressing these pair states. So one thing is, if you think about standard Rydberg dressing, when you go near basically with your laser near the single particle asymptotic, and then now check basically your figure of merit, which is something like the maximum interaction strength that you will get, like the soft core height to the decay rate that you get. If you put in all these formulas, what you get basically the graph frequency divided by the decay time or decay rate of the Rydberg state. So this bit is universal for all Rydberg, will always be there no matter what. But then you get actually a penalty factor, and because of we are in the dressing regime, this omega over delta should be actually somewhat smaller, otherwise it's not first. Yeah, so basically this scheme here comes with a penalty, and given that we do not have experimental these factors in any experiment like very large, it's like maybe less than 100 now. If this is 1/10, it's already something that you have to worry for. The nice thing is, if you go to such a scheme where you go close to a pair state, but far away from the single particle asymptotic, then actually Thomas Pohl showed already in 2015 that you basically recover the fundamental limit of all of the Rydberg is basically the round frequency of the Rydberg. I think in really please understand, but basically you forget about the single particle mixture, and what you care for is to induce basically pair processes, but the laser only talks to pair processes here. While in the first case, we talk basically predominantly to single atom processes. So that's what basically is behind basically this recovery. And then if we basically can go to the same or can hope for the same coherence pairs, then we get some resonant schemes, I would say. That was fundamental stuff, experimental stuff. So why 1%? So one is we are strongly hit by laser phase noise, and this you can actually measure by just putting a single atom and checking the lifetime of that single atom versus laser peaking. So ideally, what we recover is basically the atomic height. But what we recover, if we normalize this to the atomic time, is something that in the relevant regime actually we would like to work in at -1 megahertz. Is like more than a factor of 20 reduced compared to the ideal scenario, let's say, and we understand what it is. It's because of the UV laser and the phase noise and the Raman amplifiers and the other thing. So, and the other thing is, these experiments, they run on shorter time scales. If you have seen my background plots, there was on the scale, there was something like kilohertz. I'm talking about milliseconds. So while everyone else does resonant Rydberg physics, basically switches off the dress, does the physics switch on the dressing, and we cannot do it as people. So we get to suffer from inhomogeneous line shifts. We have quantum magic traveling and so on. And that gives us tunings also in the 10-ish kilohertz ranges at the moment. So it's also competitive. It's the scale of interaction of the spots also a lot. And the same thing is the Doppler shifts with the UV that are also magnetic. So all of them are contributing more or less equally, and we are putting out a lot of work of fighting those. The important thing is one is fundamental. Now you might ask how hard is it supposed to fight them. Okay, if you know about 99.999 something gates, it's like saying that. Yeah. So we made already progress. So on the phase noise, we are at least a factor of 4 better now. On the inhomogeneous line shifts, we work a lot on algorithms to get and feedback methods to get SLM patterns better. We want more than a factor, almost a factor 20, actually, more than a factor of 10 in inhomogeneities. So for the experts peak to peak, we are at roughly 1%, a bit lower. Yeah, and works on going also with the better cooling techniques of shifts. Let me end. Yeah, Mark showed already nice plots of laser phase noise. I want to show you basically something that I found really amazing and that's not fully understood. It's very technical. So we bought actually a new laser system from there's the company. And it's not that fun. But it's something that you can buy commercially. And what we see is basically with the same fiber cell field line, you can measure noise spectrum, phase noise spectrum, as Mark explained with our laser. So we see something like area to sideband like minus 40 dB on that line, but area to phase noise load there, something like minus 40 dB if I disregard the spikes. And now let's compare that with our old laser. So there's something seriously wrong with the new laser where we put a lot of volts. Actually, this is a theta, so yes, the old laser is more or less a theta. Is limited at the moment by our measurement dynamic range we have in the system. So there is something. I wonder what I would say. There's something that you have to keep in mind when you buy a laser from someone, and I don't know actually why this is. I have to figure out with them actually what is the reason from basically the construction of the lasers. I cannot really understand that at the moment, but there's a very strong difference in the phase noise. The different lasers here that I would not have expected at all. And that is, of course, also something that kind of adds to the difficulty that you cannot just hit on something that is good because it's the same kind of scheme of the laser still, but then you find something better. Let's go not so technical at the end. So the outlook, why we are actually interested in that, I mean, I motivated everything with a little bit of control and so on and so forth. Of course, there are quite some theoretical proposals around what you could do actually if you have this spin component fully under control. First of all, it's interesting for squeezing metrology proposals. Of course, you can combine that basically with classical algorithms to do basically resource optimization for your metrology measurements, time reversal metrology. If Tommaso somewhere there, you can do these things. Of course, quantum simulation, frustrated magnets, Benoit, and Fouquet FCP. Gauge theories. There are a lot of things that could be explored once this process is, let's say, fully. This is the team. So in Tübingen, we actually have 3 large-scale experiments ongoing now. We have this was from the potassium team, with these people actually contributing. The lithium team, that is basically a classical quantum gas microscope thing. Two-state mixture, and we have a very new experiment on strontium, which you want to put actually in the dry environment where we also body 200K use superconducting coils and other things. This is a Rydberg machine that will have a more hopefully in 1 month. Thanks.
Thank you for the nice stuff. I will start. Why did you buy the laser to start with? Did you really need it? The new laser that is giving you problems.
Well, you hope it's better than the one you had.
Yes.
And then it's worse.
Question, Manuel?
I was wondering about guessing for one. So can you specify what frequency range of the power spectrum?
Yeah. I mean, it's easy to it's even easier than the resonance physics way of Ferrari. It's basically you don't want spectral components that are effectively on resonance. So it's your delta. I mean, just assume, right? Well, you want to go a little bit in tune because of this density factor, so you want to go like 2 running frequencies or 3 running frequencies or something like this. Yeah, well, the running frequency of potassium is also continuing, but let's say it's more like 2 megahertz.
Oh.
So it comes down, it boils down to the exact same frequency range you are fighting.
I mean, like we know that it's really helpful to get this the sensitivity completely out of the circle box. I mean, if you really want
Sure. Yeah, sure.
5 to 10 megawatts, then you know.
And it's just we have already 1 watt at 286 nanometers, and that would be 50.
And what is the limit? What is that?
I don't know, it's just like such an obvious reference, right? Like your plug and play thing, you think no. So the UV laser is only this. So 1142. It's a MOGAS. Actually, I have to ask. It's a MOGAS. I'm finding out.
Over there. Over there.
Yeah, that's very good question. So, and then I was. It depends a bit of the shape, of course, of the asymptotes and the sum of all of the pair interaction potentials and the sum of all of them. What is really the spatial shape? So at the moment, the focus we are looking for is nearest neighbor. When it runs, you could in principle put a second color and control the next neighbor. But it is like the in principle answer.
Are there more questions? It doesn't look the case, so Christian is going to be all day around now, so they can ask you more.
And tomorrow, yes.
And tomorrow. So let's thank Christian again for the